Okay, so all this talk about Markov chain Monte Carlo is all fine and good, but what does it have to do with Bayesian analysis? Well, to me, Bayesian analysis and Markov chain Monte Carlo go together like peanut butter and chocolate. They're just the perfect combination for each other. So let's go through why this is the case. So remember Bayes' rule here, where we have the posterior probability is the prior probability times the likelihood divided by the normalizing constant, which when we have continuous variables is the integral over all possibilities. So remember we mentioned that this is going to be unsolvable for most problems, and this is why Bayesian analysts were kind of stuck just analyzing pretty simple problems early on. So this is where Markov chain Monte Carlo comes in. So if our Markov chain Monte Carlo model is exploring space well, then the proportion of time it spends at a value represents the posterior probability of that value. So let's see how this would work. So we propose a new value of h, so a new value for our hypothesis. Multiply the prior and the likelihood for the proposed value. If that product is greater than or equal to the current value, take that step or move on to that value. If that product is lower than or equal to the current value, follow some rules to determine whether or not to take that step, and that would depend on the rules you set up for your chain. So if that model is exploring space well, then the proportion of time spent at a specific value of h will represent its posterior probability. So we don't even need to calculate this normalizing constant, if we use Markov chain Monte Carlo processes and if they're set up well. So the benefits of that cannot be overstated. Markov chain Monte Carlo, this allows easy computation of very, very difficult problems. So problems not solvable or even fathomable before Markov chain Monte Carlo and good computing power are now they're easy to do on your personal computer. Again, the only downside is that Markov chain Monte Carlo is computationally expensive. But again, this is solved by our computing power. So now we can easily accommodate problems dealing with tens or even hundreds or even thousands of parameters, as long as the likelihood for each can be calculated and our model is set up properly. And of course, we're going to learn how to set up our models properly in this class. So this brings us to another topic that you often hear about associated with Markov chain Monte Carlo methods, and that's burn-in. So to be useful in Bayesian analyses, the proportion of time that a model spends at a value should be reflective of that value's probability. But remember that the model wanders aimlessly at the beginning and is heavily biased by where it starts until it actually finds a peak. And so therefore, we need to ignore these initial steps when we're making our estimation, because the initial steps they're not proportional to the probability of a value because they represent where our model started. And so we need to ignore them. And the number of steps that you ignore is what's called the burn-in. And of course, there's no way to know ahead of time how long your burn-in should be, so how many steps you should ignore. But it's better to ignore too many than too few. So here's again this simulation showing this idea of a burn-in. So again, this is the same model that we've been working with before, where there's a peak here, and again where that peak is changes a bit each time. But once the model gets to the peak, it bounces around that peak, but it pretty much stays there. And so once it's on the peak, the proportion of time that the model spends at a particular value is representative of the probability of that peak. But that's not true from these initial steps, right? Before the model finds the peak. And so we need to have the burn-in long enough to give the model time to find any peaks that are there. And so in this case, I've set the burn-in to just 5 steps, and the burn-in steps are indicated here in gray. And you can see we didn't exclude enough, right? So if we only excluded the first 5 steps, the relative probability of these values is going to be overrepresented because the model was here not because they have a high probability, but because that's where it started. So we need to ignore more steps in this. So here's another example where the model found the peak, and once it finds the peak, the proportion of time that it spends at a value is it's relative to the actual probability of that value. But again, it takes the model a while to find a peak. And so in this case, we had set the burn-in at 10, and that wasn't enough. But 10 probably would have been enough in this case, but not in this case. So it depends on how long it takes your model to find the peak. In this case, the burn-in was 100. And so in this case, that burn-in's long enough, right? So the whole time the model spent finding the peak is gray, so we're going to ignore those steps. Whereas once it found the peak, now those values should be representative of the probabilities. And here's one where the burn-in was 500, so the same thing. Clearly, these steps taking for our model to find the peak aren't included in our estimates, but once it found that peak, it stayed there, and so the proportion of time it spent at these values should be representative of those probabilities. So again, you can use the same functions that you had before, but now we can set the burn-in to different values to see how it looks. So again, you've already sourced the scripts, and so you can use the one-peak MCMC function, and you can play around with different steps, different degree of heating, and now different burn-ins. So I'm just going to play around with some here and see how this looks. So let's say that now I'm going to do it for 1,000 steps. I'm going to set the heating to 0.3 and maybe the burn-in to 100. So let's see what that does. So in this case, we did pretty well. So maybe our burn-in wasn't quite long enough, but you can imagine if our chain started over here just by chance, 100 would have been plenty long. But because our chain actually started kind of far away from the peak, then we needed to include a burn-in of longer. But again, it still found the peak and then just bounced around that peak. So those the proportion of time it spent at each value should be proportional to the probabilities. So I'm going to change this a bit. And so if we have a longer chain, we can afford to have a longer burn-in. So I'm going to have 5,000 steps here, and now make 1,000 steps the burn-in. And let's see how it does there. Yeah, so there you can see plenty of time for the model to find the peak. That was our burn-in, so we would have ignored these steps that are in gray. And then there's plenty of steps where we recorded the data to get good estimates of those values. So again, I'll stop the video here. Once I'm done with that, you guys can play around with different lengths of the chain, different burn-in values, and different heating values, just to see how they work together to see how the model, or to determine how the model explores parameter space.